Good morning, everybody.
Morning.
How's it going?
Okay.
Okay, wonderful. So, yeah, I hope you had a nice Veterans Day. Anyway, so what's the program for today? We will finish chapter 10, which will be essentially discussing a little bit again the relationship between the width of an interval and sample size. And the reason we will discuss that at the end of chapter 10 is that last thing that I want to show you, which is how to determine beforehand the sample size that you want to take. So you want to do an experiment, and then you know what significance level, respectively what confidence level you're looking for. And you also have an idea of how wide your interval is supposed to be. There is a triangular relationship. So, and I told you before, two of those three determines the third factor. So, for example, if you know the sample size and if you know the confidence level, I have shown you so far how we can calculate in an interval estimator. So we can, calculate the boundaries of that interval. Technically, if you know the sample size and if you know the width of interval that we want to produce, we could then just, calculate the confidence level once we have the interval. So you would essentially take your sample, then you have your sample mean or sample proportion is essentially your point estimator. And then, as I said, so if you know the width of interval, you can just build the interval accordingly around that sample mean. And then you can essentially calculate it back to see how many z-scores is it away, and then you can look in the table, and then you know what's your confidence level. But that's actually a case that doesn't happen really in reality. That second case, that's what we are not discussing it in the chapter. But the third one might very well happen in reality. So you might have to estimate something, and you you know what confidence level you're looking for, and you have an idea of how wide your interval is supposed to be so that your result is useful. But you want to determine, okay, what's actually the sample size that we need in order to be able to come up with a usable estimate. We have 1 minus alpha, which is my confidence level, right? That's the probability that essentially the population mean is within the range of the interval that we are building. Alpha was the significance level, which means 1 minus alpha is the confidence level. So the probability that we are correct. And alpha is the probability that we are wrong, which was the significance level. So when we have proportions, this is the interval that we will be building. So this is how the interval looks. So p hat minus z of alpha half, etc., all the way to p hat plus z of alpha half, etc. So for example, if you're building a 95% confidence, as I mentioned before, that interval width is very important for us, right? So if you come up, for example, with a election estimate and you say with 95% confidence, the proportion of the voters who intend to vote for, let's say, Donald Trump are between 9% and 88%. I mean, yeah, great. That's not very useful, right? Coming up with such a wide interval. It doesn't contain much information. But if you come up with something like between 52 and 56%, that's something a lot more useful. So that width of interval is very important. So oftentimes, obviously that confidence level is very important. That's very clear, but also the width of interval is very important. So oftentimes the variable that we want to play around with is the sample size, right? So we don't want to sacrifice in significance level and or respectively in confidence level and in the width of interval, but we can, make some sacrifices in sample size in the sense that, we are willing to accept a higher sample size, but not give up of the two other factors. And now if we look into it, the relationship, the width of the confidence interval is a function of a couple of things. One of them, it's a function of my confidence level. So depending of that alpha, the smaller that alpha, the wider that range will be, right? Because the smaller the alpha, it means the higher my confidence level. The higher the probability that I'm correct, the smaller the probability that I'm wrong. So the wider is going to be that interval. On the other hand, we have this other factor that plays a role, which is the sample size. And a third factor is actually also playing a role. I'm not emphasizing it that often in the class, but because we don't have an influence on that, but you should be aware of it. The standard deviation, respectively the variance of the population, which is essentially this expression p hat times 1 minus p hat. So this p hat times 1 minus p hat, this is essentially, if you remember, the variance of the population. So the square root of that is the standard deviation of the population. That also has an influence on the width of the interval, obviously, but we have no influence on that. But we do have an influence on this one, right? On the sample size. So again, the confidence level has an influence on the width. You can see it here graphically. So here we have a confidence level of 90%, then the boundaries would be from the one red line to the other red line, because we're cutting off a 5% tail on each end, a larger tail that we can cut off, which means the part that remains in the middle is larger, versus a confidence level of 95%. We have to cut off smaller tails. We can cut off only 2.5% tail on each end. So what remains in the middle is larger. So we are looking at a larger interval, which is from the one blue line to the other blue line, versus a smaller interval from the one red line to the other red line if we decrease our confidence level from 95% to 90%. Okay, we can define essentially, now let's take a look on how to calculate the sample size. So first of all, as you know, we are facing that sampling error. So every sample that we take, the mean of that sample is going to be slightly different than the mean of the population. And that difference between the means is called sampling error. And they call it also error of estimation. So they mean the same thing. On the other hand, we know that for proportions, for example, we have that confidence interval of 1 minus alpha. And the confidence interval 1 minus alpha is essentially, yeah, we know that the probability of, so this is from the z-score formula, essentially derived directly, okay? So minus z of alpha half, so essentially how many standard deviations to the left of the mean and how many standard deviations to the right of the mean defines the probability of me being wrong with my estimation, okay? So it determines the interval width. And this is just the value that we have from the z-score formula for proportions. Now, all we need to do is here multiply both sides with what is in the denominator, which is the square root of p times 1 minus p divided by n. So if we multiply all three parts of this equation with what is in the denominator, what you have here is this expression smaller than this expression, smaller than that expression. Now let's focus on the expression in the middle. That's p hat, which is my sample mean, minus the p, which is the mean of the population, the true mean of the population, okay? And remember, that's exactly nothing else than our error of estimation or my sampling error. So this is my sampling error or error of estimation. So this thing is essentially the estimation error. The estimation error is nothing else than the difference between p hat and p, which is between this and that. So, and these two are symmetric, right? This is my z alpha half blah, 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 blah. This is minus blah, 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 blah. It's minus exactly that, right? So we can make things simpler. We can see that it's the same thing as saying the absolute value of the estimation error must be smaller than this thing, z of alpha half and so on and so forth, right? The absolute value of the estimation error must be smaller than that, okay? So that's essentially, if you want, this value represents half of my interval width pretty much, right? If I can just say essentially the absolute value of my estimation error is smaller than this, half of the interval width, So what we can do, we can just assume this is equal b. Okay, b is like the bound of the error of estimation, right? So the limit, like how far is the limit away from the mean, essentially. That's what b represents. Okay, and once we do that, now we can very easily determine my sample size by solving this inequality, this equation with respect to n. Solving this equation with respect to n gives me a formula where all I need to do is plug in those values, and then that gives me the sample size that I need. Okay, which would be this formula. So this is the formula for proportions. Now, if you want to calculate sample means, obviously the formula looks a little bit different because the formula for means was different. The basic idea is the same, but the formula is slightly different. But for proportions, we already have this formula, and all we need to do is plug in the numbers and calculate. Now, here's a little problem that we have. We do know this, that's our confidence level. We actually determine this. We also know B. B is essentially half of the interval width, right? So we know that as well. That's nice. We know this and we know that. We have a problem, however. We don't know P. P is the true mean of the population. We don't know it, right? So that's exactly what we actually want to figure out by taking the sample. We are taking the sample to figure out what is actually this P, the true mean of the population. So what to do when we don't know P? There are two methods to go, essentially. There are two methods. So here's just an example of how you can calculate, those numbers, etc. Just plug in those values, etc. But so if you don't know P, um, two methods. Method number one is if you have no idea what P could be. You have absolutely no freaking idea. If you do that, then we choose the value for P so that it gives me the worst case scenario, essentially the scenario where I would need, at which I would need the largest possible sample size. And if you remember from a few chapters ago, we talked about it a little bit. We talked about, because this thing underneath the square root here is actually the variance of the population, right? When you take the square root of it, it's the standard deviation of the population. So this thing is standard deviation of the population. If you look only on what is underneath that, this p times 1 minus p is the variance of the population. So we essentially assume the population to have the highest variance possible. And what is the highest variance possible of the population? It's when p is exactly at 50%. That's the highest possible variance, right? Um, so in that case, we just go with P of 50%. So we go essentially super conservative, and we plug in the values and we calculate. Now, here's an example. 1.96 means my confidence level is what? That's for 95% confidence level. Remember, because it means that's the value for 2.5% on each tail. You're cutting off 2.5% on each tail, on both tails. So what is in the middle is 95%. So my confidence level is 95%. My B is 0.03. So the total interval width is 0.06. Okay. And for P, I just assume 0.5. If P is 0.5, 1 minus P must be also 0.5. And then you plug in those numbers and you calculate it and you get, this is essentially the sample size that you need, 1,068. Now this is very conservative. This would be the sample size that you need if P is exactly 0.5. If P happens to be any other value, the further away is the P from the 0.5, the smaller does that sample size actually need to be. So this is your conservative estimate, which means for any other P, you will achieve either a higher confidence level than the minimum that you wanted, or you can achieve a lower interval than what you wanted, or you can choose to go with a combination of both. So a little bit higher confidence level and a little bit, let's say, lower interval width of your estimation. So you can choose how you use it to your benefit with the higher sample size. But then at least you have an idea of the sample size that you need. Well, that's okay. That's again very conservative. So you probably need less a sample size less than this, but it does give you an idea. Is that clear? Please give me a thumbs up if that is clear. Very good. So any questions for if anything is not clear? Oh, excellent. Okay, guys. So method number 2 is if you have a guess. Okay, so if you have a guess of what's going to be P more or less, then you can go and insert that P, which is your guess, to see what sample size you need. Okay, well, the good thing with this method is that the number that you get out will be much smaller than the previous method, right? So for example, here we go again with the same numbers, right? We are looking here again at a 95% confidence interval, level. And the width of the estimation interval is again 0.03. But because we enter for P value of 0.2, 20%, the result that we get is, a much smaller sample size, 683 only, instead of, what was it before, 1,000 and something. So that's nice, right? It gives us a smaller sample size. The only problem with this method is if we are wrong, it depends how we are wrong. If you're wrong in the one direction, in the sense that P ends up being smaller than the 20%, so further away from the 50% that what was our estimate, we are still fine, right? So we still, had a sample size that was actually too much. But if you're wrong in the other direction, so P happens to be larger than 20%, then this sample size is not enough to achieve that confidence level and the interval width that we wanted. Okay, this would be then too small. That would be a problem for us. That's why if you do an estimate, you should go, conservative, in the sense that, your estimate is the closest value to 50% that you think the population proportion would be. Okay, so if you are, for example, you're not sure, you think it's somewhere between 20 and 25%, then you should go with the 25%, because that's the more conservative estimate that will generate a larger sample size, but then okay, this sample size is going to be enough. Okay, is that clear, ladies and gents? I guess that's a yes. If you're looking at population means now instead of population proportions, as you remember, the formula is slightly different. So again, population proportion, what I discussed in the last couple of minutes was, for example, if you look for the question, what percentage of Castle language students are, let's say, female, or what percentage of Castle language students own a car, or something like that, right? So it's like a binary answer. It's like a yes or no. What percentage is this? What percentage is that? But if when we are looking into proportion mean, we are going after a question, something like, what is the average income of the Castle language student? What is the average height of the Castle language student? How many bicycles in average does a Castle language student own, or something like that, right? So, and then as you remember, the formula is a little bit different. It's this thing. But the principle, the way you work, is very similar. The width of my confidence interval depends on the confidence level, population standard deviation, and the sample size. So we have to again transfer the formula, and the way we do it here is this. So again, that B is going to be now this thing. That's again half of the interval width, if you want, right? It's this thing, and all I need to do is solving it with respect to n. And when I solve it with respect to n, this is going to be the formula. And all I need to do is plugging in those values, essentially. Yeah, so here's an example to illustrate. Suppose that in example 10.1, before gathering the data, manager had decided that he needs to estimate the mean demand during lead time with the 16 units, which is bound to the error of estimation. N must be an integer, and we want to bound on the error of estimation to be not more than 16 on any of those. So the thing here is that we have to kind of estimate the sample, the population standard deviation. So we have to come up essentially for the value for sigma. That's the only issue. But other than that, and again, here we should also go again conservative in the sense that we should take rather a higher number, right? To make sure that definitely our sample size is large enough. And that's pretty much it. That's just the formula that we use in this case.